Why are absolute value inequalities important for calculus convergence? Imagine trying to measure how close a series gets to a certain number when you add up infinitely many terms. That's where absolute value inequalities come into play. They help us understand the size of each term, no matter if it's positive or negative. Think about the inequality like this. How far is a number from zero? That's what absolute value measures. When solving inequalities like the absolute value of x minus 3 is less than 5, you're finding all numbers within 5 units of 3. This idea of measuring distance is key in calculus too. In calculus, especially when dealing with infinite sums called series, knowing whether a series converges is vital. Convergence means the sum gets closer and closer to a specific number as you add more terms. But sometimes, a series only converges when you look at the size of its terms, ignoring their signs. That's called absolute convergence. It's a stronger condition. If the sum of the absolute values of the terms converges, then the original series converges absolutely. Absolute value inequalities help us compare series. For example, if the absolute value of each term in a series is less than some number, and the sum of those numbers converges, then the original series also converges. This is called the comparison test. It's like setting a boundary for the size of each term, making it easier to see if the series will settle down to a specific value. Why does this matter? Because if a series converges absolutely, you can rearrange its terms without changing the sum. This is not true for series that only converge conditionally. Rearranging a conditionally convergent series can actually change its total, which can cause mistakes in calculations. Absolute value inequalities also show up in integrals. For example, the absolute value of the integral of a function is less than or equal to the integral of the absolute value of that function. This helps us estimate how big an integral could be, especially if the function oscillates or swings between positive and negative. For learners, understanding absolute value inequalities is like building a bridge from solving simple algebra problems to tackling more advanced calculus ideas. They teach you to think about size, distance, and bounds, which are essential when working with limits, series, and integrals. Mastering these inequalities early on makes it easier to grasp why certain tests for convergence work and how to handle infinite sums and integrals safely. In practical terms, these ideas help in estimating errors, analyzing signals, or understanding oscillating functions. For example, in physics or engineering, you might use these concepts to make sure a sum or integral representing a physical quantity is reliable and meaningful. Whether it's modeling sound waves or electrical currents, knowing how to compare sizes and bound values is key. To sum it up, absolute value inequalities are important for calculus convergence because they give us the tools to judge whether a series or integral behaves predictably. They help us use comparison tests, ensure that rearranging terms won't change the sum, and provide ways to estimate and control errors. Learning these concepts in algebra sets the stage for understanding the deeper ideas in calculus, where the size and behavior of infinite processes matter most.